Alright, so today we'll get into energy and we're going to really get into the meat and bones of the topic. We're moving from, just simple ideas of energy and photosynthesis to carbon and its allotropes. And that's where we're going to focus for quite a bit of this topic, especially leading up to the yearly exams. Okay, so let's go. By the end of this, you should be able to relate the position of carbon on the periodic table to its number of protons, electrons. And you should be able to do this already with its nuclear properties. You will be able to explain the term allotrope, and you should be able to explain the structure of carbon, of three main allotropes in particular, to their bonding. Now, if you have a look over here, here are eight of the main ways that we can see carbon. Now, these are the most common ways. There are a couple more. There's lots of different types of, there are lots of allotropes of carbon, and we'll get into what that is in a second. Okay, but first, carbon and the periodic table. Okay, so it's just, we'll get a little highlighter over here. You can see carbon's right here in group 4, and it's got obviously 6, its atomic number is 6, which means there's 6 protons, 6 electrons. The atomic mass is 12.01, which means it also, on average, has 6 neutrons. Okay, so it's a non-metal element. Cool. It has 2 electrons in the first shell and 4 in the outer shell. Now that actually gives it a very weird valency. It gives it a valency of ±4, so it's got a bit of variability in how it reacts. So its electron configuration is 2, 4. Pretty straightforward. And here we see it. So we've got, here's the 4 valence electrons, and that's a neutral carbon atom. All right. So allotropes, what is it? Well, basically, an allotrope is a different structural form of an element. Now, they're made of identical atoms, okay? And this can give quite massive variation. Like up here we see carbon, and this is also carbon. This is graphite, it's coal, and this is diamond. So here's graphite, and it burns and all sorts of wonderful stuff. And here's diamond, which will also burn, but they're very, very different. But they're made of identical atoms. They have identical chemical properties, okay? They do have different physical properties, and that's what makes it so spectacular. For example, if we just quickly compare diamond and graphite, they both combust, forming carbon dioxide. It's the same chemical reaction. However, their physical properties are hugely different. Diamond is much, much more dense than graphite. Diamond is an extremely poor conductor of electricity, which we'll see why in a second, whereas carbon's a very good conductor of electricity. Diamond is extremely hard. We say it's the hardest natural substance on Earth. Just waiting for the bell to go. And we say graphite's quite soft. All right, so how does it get there? So let's have a look at the 3 allotropes of carbon that we're going to focus on in chemistry this year. So we've got diamond. All right. So diamond is a macromolecule with each carbon attached to 4 other carbons. Okay. So it's a tetrahedron. So we go there, 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 there. That's that central carbon. It's a covalent network molecule in the tetrahedron shape. The tetrahedron, it's a triangular prism with a carbon in the center and a carbon at each point on the triangular prism. And here's a good diagram. See, the carbon's right in the center. It goes boom, boom, boom. This angle here is 109 degrees, but the angle caused between these is 60. Hence the triangle. 3 of those add up to 180. But that's 109 degrees right there. So strong covalent bonds throughout. Now, what does this mean for carbon? It means it's very hard. For diamond, it means it's very hard. It means it has a high melting point and a high boiling point because it takes quite a lot to change that state. And there's no free electrons. And this means it is a very poor conductor of electricity. All right, that's diamond. Now we look at graphite. Now here's the structure of graphite. We see these flat hexagonal sheets, okay, that are laid on top of each other and held together by what we call van der Waals forces, or as far as you're concerned, weak dispersion forces, which we'll see in a second. But if you have a look over here, just before we get into our notes, that one there, it touches 3 carbons. And every single carbon touches 3 other carbons. There are 4 valence electrons, so that actually comes into it in a second. All right, so again, macromolecules. There are hexagonal bonds. Each carbon atom is bonded to 3 other carbon atoms. strong covalent bonds in that hexagonal layer. The hexagonal layers are then held together sitting on top of each other by weak dispersion forces. So what does this mean? Well, basically, hexagonal means that only 3 of the 4 valence electrons are used up. There is a free electron for every atom that conduct electricity. Weak dispersion forces means the layers can slide. Graphite is very soft. This is why we use it as a lubricant to allow things to slide between each other, or for writing, because you can just push it down and layers will go along the paper. Fullerenes, or Buckminster fullerenes, or buckyballs. This is the 3rd time I've tried to film this, because buckyballs, Buckminster fullerenes, and fullerenes have led to a few inappropriate videos through accidental swearing. So, also known as buckyballs, basically you have 60 or more carbons arranged in a hollow sphere, like this, okay? It's 60 or above, so C70 is also quite common, C60, C70. Now, you'll see that you've got the hexagonals joined together to pentagons. So you've got a pentagon in the center, or pentagonal bond, with hexagonal rings all the way around it. That's pretty straightforward. You'll also see that there are these lines here. Now these are double bonds. Now we'll get into this more in a future video, but what that means is that between this carbon here and that carbon here, they're actually sharing 2 valence electrons each. And this means that there are no free electrons. So it has an open structure, very low density, and there are several future uses. For example, they may be useful as semiconductors or lubricants. Nanotubes are part of the fullerene family, and we see one here. Now, these are insanely interesting and really useful for lots of different applications, although none on a large industrial scale yet. And here we see a nanotube spinning around, and then we move off to, this is what it looks like. So it's not black, it's not clear, it's actually, this is always in solution with olive oil, interestingly enough, and here we see it as a purple color, and that's what color it is. Alright, so that was it. I hope that was interesting, and now next we'll move into carbon compounds and hydrocarbons, and we'll move further down there. Okay, see you.